see what you guys said. So we're doing the Bandit simulator. Remember, the Bandit simulator looks something like this, right? We have the 4 choices. In general, we have L choices, and you can choose which one you want to go to. And what you're trying to do is figure out which lake is the best. Maybe this lake is the best, so I'm just going to go to this lake forever and hope that I got it right. And then at the end, I will see if it is better or worse. And that's the question, is like, how do we balance exploring versus kind of playing what we think is the best? So how do we balance greediness with exploring? And the way we're going to measure it is this regret. So this is, I think, the very last thing I defined last class. The regret is how much worse the arm is than the best arm on average. And of course, in real life, you never get to see this. Maybe if you're lucky, you get to see it at the end. So the regret is some kind of like hypothetical thing. I guess in my situation, the computer tells me the regret. So it turns out the best arm was A. I should have been going to A the whole time. And the advantage was 1.125. So B, C, and D were all on average worse than A by 1.125 fish per click. If I had gone to A more often, I would have done so much better. And in fact, the AI went to A 26 times out of 40, even though I went to lake D the most, which was a poor decision, not a very smart idea. So that is what we were doing, and we had this notion of regret. And then the question for you was, what is better? What I just did is the random 1 strategy. Pick a random arm to play, then play it T times in a row. That's the random 1 strategy. I guess actually I didn't do the random 1 strategy because I played them all once. So this is like, play them all 0 times and then go. So it's like you're feeling lucky, you just pick one at random and go. All right, my screen keeps turning off here. Let's see if it's going to do it again. Okay. So that would be like the random 1 strategy is like, I'm feeling lucky, let's go with option C. Okay, we did it. Hey, look at that. The best lake was C. I got 421 fish, and the stupid AI only got 378. I'm so much smarter than the AI. I got 1.25 extra fish every time. I went here 40 times. I got 0 regret, right? The regret is, in this situation, it tells you the regret is 1.25 for arms A, B, and D. Option C is the best. Option C has 0 regret. My strategy worked perfectly. I got the best possible result, and I got 0 regret. Amazing. So is that the best strategy? We're going to find out. Okay, so you had to compare that strategy, which was the random 1 strategy, or you could do the pure random strategy, where you like roll a little dice and you decide which of these 4 you want to do randomly every single time. I think you were doing this last time, right? When we were voting, you were picking a new random arm every time to vote for? Yes, okay. So this is like another thing you could do, randomly pick. Okay, let's see which is better. Question before I reveal? Yeah.
You beat the AI?
I beat the AI, yeah.
No way.
Yes, I did it. Oh, were you gone when I did it?
I think so.
Yes, I used a really smart strategy that worked out perfectly, yeah.
Does that say the AI only went to Lake C twice?
It only went to Lake C twice, yeah. That's right. The AI got bamboozled, yes. So here's the thing, no matter what strategy you do, sometimes your strategy will work, and sometimes your strategy won't work. It's going to turn out the strategy you pick a random one is not a very good strategy. Well, when we analyze it, you'll see it's not a great strategy. And the thing the AI does is, in some sense, the like best possible strategy of all strategies. But even that one, if you only play 40 times, maybe you get unlucky and you end up getting a bad outcome. So yes, it's true. There is quite a bit of luck here, and that's why we are not trying to maximize the reward on one run. We're trying to do this expected total regret. So the total regret is like how good or bad your run went, and then on average, how good is your strategy? That's what we're trying to do. Okay, so those are the 2 options. Let's see what you guys voted for. Which one is better? Which one is worse? All right. Ooh-hoo. Okay. So 8 people think they're equal. 4 people think the random strategy is better, and 3 people think the random 1 strategy is better. I'll tell you one thing that's different about the 2 strategies, for sure, is this outcome of having 0 regret, the best possible run you can get in terms of regret. I just got the 0 regret run. That is impossible to get if you do the play all of them. Because if you play all of them, you're going to play sort of each of them about 25% of the time, then you're definitely going to pick up some regret. So shouldn't it be that this is like a really good, this is the best possible outcome? In the other situation, you cannot achieve this. So isn't this better? Yeah.
The way I thought about it is
that over one game, yeah, that's strategy different. But if you play 4 games, they're effectively equivalent because you're choosing randomly in the first, so they're effectively the same strategy.
Yeah. So okay, so this is very good. So I think the operational keyword is to think of expected total regret. So even though sometimes this strategy achieves 0 regret, really good, sometimes it gets a horrible regret. Like I could have picked the worst arm, and then I would have gotten the maximum possible regret. So even though this strategy sometimes gets 0, it sometimes gets the maximum value. We don't care if it gets a high score and a low score. We care what does it get on average. That's how we're measuring if these things are good or bad. And on average, as most people figured out, the two strategies are exactly the same. So on average, they do the same thing. They have different variances. So like I said, this one, the random once strategy, that one can be the best possible. It can also be the worst possible. Whereas the pure random is sort of like consistently middle of the road, but they have the same average. And in fact, let's write down what that average is and sort of analyze it. Like what does it look like mathematically? So these are the first two strategies we're going to analyze, and we're going to try to improve on them. So let's say the random once strategy. Actually, okay, before we do anything, why don't we do a little simplification over here? And I think I wrote this one on the board last time, is we can write down the total regret, the expected total regret. So you could write this like this. It's the expected value of the sum from lowercase t equals 1 to capital T of the regret of the arm you play at time t, right? Okay. But you could rearrange this, and I think this is a useful way to rearrange things. Instead of thinking about which arm did you play on the first round, which arm did you play on the second round, let's just count the number of times we played each arm. So rearranging the sum, you can write it as a sum over lakes. So L goes from 1 to capital L of the number of times you played Lake L times how bad the regret is at Lake L. So I'm rearranging the sum. Instead of summing up in time and summing up Lake 1 plus Lake 1 plus Lake 1, just count up how many times did you play Lake 1. Let's call that N and add it up that way. And the randomness is only in the number of times each thing is played. So you could write it like this. It's 1 to L of the expected number of times you play an arm. So this was an equation from last time where here NL is the number of times you play Lake L. Okay, and I guess I'm doing a loosey-goosey thing. We had the two analogies, right? One analogy is you're on a fishing trip and there's lakes, so I'm using L for lake. But the other analogy is it's a multi-arm bandit with lots of arms. And so I'm probably going to refer to both. Lakes and arms, they're both the same. Has anybody been to Algonquin Park and there's a big lake called Lake Opeongo? And that lake has arms. So that's like the optimal, that's like the place I'm talking about. Okay, so, all right. So what's the point? The total regret just depends on average, how many times did you play each arm, weighted by how bad that arm is. And the two strategies we talked about, they actually do the exact same thing for the expected number. So the random once strategy, the random once strategy, what does it have? It has the expected value of NL is always capital T over L, right? So how many times do you play an arm? Well, if that arm got chosen at the beginning, that happens with chance 1 over L, you play it T times. I guess I can write out even more specifically. It's either 0 or T, and it's 0 most of the time, and it's T with probability 1 over L, and it's 0 with probability L minus 1 over L. And so its average is T over L. And the other random strategy, what do I call it? The pure random strategy. Pure random. That is also has the same expected value. The number of times you play each arm is also T over L. And that this time they're binomial. So I guess they're binomial, and there's T of them, and they're chance 1 over L, but same thing. So even though you have different distributions, the averages are the same, and that's the only thing that matters for the regret. And so they both have what is the regret, or the average regret, the expected total regret. Total regret. It is the sum of T over L times T over L. Let me erase this. T over L times delta L, summing from L equals 1 to L, which you could write like this. It's T times, and then you have this constant, 1 over L, L equals 1 to L of delta L. This thing is the average regret of the arms. So arm1 has an average, arm2 has an average, all the way up to arm capital L. This is summing them up and dividing by the number. That's the average regret of the arms, and it is a linear in T. So the longer your fishing trip, the more regret you have. On average, you double the length of the fishing trip, you double your regret. So this is linear, and the slope is the average arm regret, the average of the deltas. Okay, very nice. So really what we're going to be doing now is thinking of smarter strategies, and we're going to try to make our strategy not linear in capital T, but sublinear in T. So can we have an algorithm that as T increases, the amount of regret you have increases slower than T? So you like double T, but you don't double your regret. We want to go on a really long fishing trip and not like have super high regret. So that's the idea. So, and it turns out linear, this kind of linear is quite bad. So can we beat it? Can we do better? Okay, and the first thing we're going to try, these are all the suggestions from last class. We're going to do this idea of first we're going to explore for a bit and then go greedy. So instead of just picking one randomly, let's do something like this. Let's try an explore then exploit. Explore first, then exploit. Okay. And so what we're going to do is we're going to have this two-part strategy. First, we're going to play each arm equally. So play them all a few times, and then we will go greedy. Then go greedy. Play the best arm so far. Go greedy. And to show you an example of what this looks like, let's pretend I was doing this with 8. So if the number of times we explore is 8. Then I will play each arm twice. So 1, 2, 3, 4, 1, 2, 3, 4. I've played each arm twice. I've played 8 exploring rounds. That was my exploring. And now I'm going to go greedy. So whichever has the highest average, I'm going to pick. Option D has the highest average. So the rest of my fishing trip, I just go D, 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 D. And then it turns out the best lake was Lake B, and I screwed up, and I am very sad. So that is the explore, then exploit. Okay. So that is what we want to do. We're going to do this one n, lowercase n times. Lowercase n times total. And then that means we're going to go greedy for t minus n times total. Okay. Explore and exploit. And to show you guys what this looks like, actually, let's do the analysis when n equals 1. Let's analyze this. And by n equals 1, I guess I want n equals L analysis. So that's when you play each arm once. So you play each arm once, and then you go greedy. Here is what I claim the analysis is. Actually, why don't I just show you the slides? Okay. So here's the strategy we're doing. We're going to play each arm once, and then we're going to go greedy. So in the first L rounds, the regret is at most 1 per round. I'm going to assume that there's some fixed constant that is bounding everything. This makes things a little easier to analyze. It lets us put like constants in front of everything. Let me go to the assumptions over here. So here are the assumptions I'm making. There's a definite maximum and minimum payoff. This is really important if you're playing a game where there's like one arm has like infinite regret or something. That's like you can't really analyze what's going on. So we're going to assume there's some maximum minimum amount, and we're going to, without loss of generality, assume it's between 0 and 1. This is really helpful for like games. In a game, like no matter how badly you play the game, you lose the game, you get -1 reward. So it can't be worse than that. And here are some of the notations we've done already. So there's NAT, that's the number of times we've played it. The T means up to time T. Delta A is what we had before. And the mu's are the means, L and T we did. We're going to get to the average and some constants over there. Okay, so what were we saying? All right, this is the strategy we did before. T times that average, very nice. Now we're doing this strategy. So you play each arm once and then go greedy. So in the first L rounds, the explore phase, you pick up some amount of regret. And the amount of regret you pick is bounded in this phase by L. Okay, so n total times each. This is important. N is the number of times you play each one. So n is the number of times you play each one. And then this is n, t minus nl, and this is L times n. So the when n equals 1, not n equals L, we have two types of regret. We have the explore regret, which we pick up L regret, L. And then we have the exploit regret. So when we go greedy and we're exploiting, how much regret will we have? Well, hopefully it'll be lower than before. And here's a quick little analysis. It's some little probability calculation. So we have these random variables, x1, x2, all the way up to xl, which are how many fish we saw. So let's show you what this kind of looks like, right? So restart this. We do each arm exactly once. And I have these four numbers, 10, 3, 5, 3. Right? I saw each lake happen exactly once, 10, 3, 5, 3. And those are my numbers. Now I'm just going to pick whichever one is the best and play it over and over again. So those are my numbers. How much regret do I get? So the number of times you play each arm is this quantity. You play every single arm once, and then if that number is the maximum, then you play it t minus 1 more times. If that number is not the maximum, you play it 0 more times. So on average, you get 1 plus this probability. So in this situation, the number of times I will play this arm, right, it's just a chance that this x1 is bigger than x2 and x3 and x4, right? So if A is the best arm, then hopefully this is like a pretty high probability to be the largest, and then I'll be quite happy. Okay, so let's see what that looks like. So the total regret is the sum of this number over all the delta A's. And you can analyze this in a number of ways, but the thing that I want you to notice, it is still linear in T, right? So after you factor out the T's, what you're going to get is some constant over here, that constant C2. It's something to do with this 1 plus. This 1 plus pops out. You also have a minus 1 over here. So there's some funny constant in front. And there's some slope. And the slope has to do with these probabilities and the delta A's. But at the end of the day, it is still linear. And I can show you a little simulation of what this looks like. So it's a linear function. And here's my simulator. Yeah, here it is. So here are the two situations. The blue line is the pure random, where you go all the way up. And the orange is the random once and then greedy. And so because in the first round, I think there's 20 arms in this game. So in the first 20 rounds, we're going pure explore. We pick up a little bit of regret on this line. And then we are still linear, like this. And it is a linear function. It has a lower slope than before. So we kind of like are doing a lot better. But at the end of the day, it's still a linear function. It's just that it's the total regret is not a linear from 0. It's like up a little bit and then over. So still linear. Okay, that's the analysis sort of the random once and then greedy algorithm. Yeah, in this situation, there's 20 arms, so 20 choices, which is why the first 20 rounds we spent exploring. Okay, so still linear. So our goal, the goal I said before, was can we beat linear? And we haven't done it yet. Can we do better? So in some sense, we've done better, but in another sense, it's still linear in T. Can we do better? Can we get sublinear in T? Sublinear in T. Okay. All right, let me put this thing back up. Any questions or comments so far? Yeah.
Is that a simulation with, like, let's say the arm that you initially pick,
Yeah.
it actually drops below the other arm, and you switch to that?
Oh yeah, okay, this is a good point. So in the analysis of the algorithm I did over here, this is a great concept. I said you pick whichever is the maximum, you play that one forever. So you don't switch in the way we've analyzed it. In the actual simulation, I have switched. And the reason is it's a lot easier in the code to just take the maximum. So if you read the code over here,
So wouldn't that make it like a bit less than
Yeah, and actually what you've explained is why is it, I said in the analysis it's purely linear. But if you look carefully over here, there's a little curve. You see this like little tiny curve right here? So what it should be is it should be straight and then it should go like linear like this. And because of this like sometimes like there's a 1% chance you actually end up switching arms, that makes it a little bit better. And that's why it's like curved down a little bit over here. So the algorithm I said should be like perfectly straight, like a line. That was the analysis we did. And what is actually plotted is a little bit better because of the reason you said, and that's why it's not perfectly straight. Yeah, that's a good point. Of course, in real life, it always makes sense to do what you're saying, right? Like, why wouldn't you pick, if you're being greedy, you pick the actual best one, not the best one we determined a while ago. Yeah, that's a great question. Any other questions or comments? Okay, so here's the question for you guys. We're going to try to improve this, and we're going to try to improve it by increasing n. So we're going to increase n. So instead of exploring just with n equals 1, can we explore more? So we did the analysis for n equals 1. You picked up L regret over here. The exploit regret was these probabilities. So it was the sum of the probabilities that XA is the maximum, max of one sample, and that was multiplied by the delta A. So it was this kind of average. That was times T. That was the average over there. I guess there's no 1 over L. Okay. So that was the exploit. So it was some constant, but then still linear in T. And the question is, if we choose a different n, can we make it better? So choose a different n. And the idea is if we choose a different n, we can sort of hone this average in. This average will get more and more concentrated on the best arm. So the arm that is the actual best one has a really high chance of getting chosen, and then we pick up a really small number of regret. So can we shrink the slope of this line by choosing a larger n? And as a little fun example, I'm going to say, let's pretend t equals 1,000. What should n be? Okay, and I have this, right? That matches the little simulation. So in this simulation, it was 1,000 rounds. There were 20 arms, and this is the average regret. How big should n be? So this was n equals 1. It was like this. Can you make n bigger or smaller and make it, I guess you can only make it bigger. Can you make it better? And I made this just for fun on Mathematize. You guys probably won't have a sense, but I mean, just imagine you're playing this thing. Instead of 4, there's 20. And instead of playing it 40 times, you're playing it 1,000 times. How many times do you want to explore each one? Okay, and in Mathematize, I have this as a little question. What should n be? Okay, so t equals 1,000. We're trying to explore the exploit strategy. How many rounds do you think it's best to explore? N equals question mark, and just put in your best guess of what you think n is.
You said there's 20 lakes, right?
There's 20 lakes, yeah. So this is n is the number of times you do each lake. So if you put in n equals 2, you spend 40 rounds exploring.
And then that is, we explore each lake n times, right?
That's right, yeah.
You posted, are you going to post the slides that you have?
I can post them, yeah, sure. Okay, since this is kind of just for fun, there's no right or wrong answer really. I'm going to put a timer on you. Okay, let's see what you said. N equals how big? Okay, a couple people in 100, 5, 10, 20, 18, 35, 50, 250, 300, lots of numbers. And that's what I have over here. In the next thing, I have a lot of different answers. Let's look at them all. So here is a whole bunch of different numbers. You can look at what number you were closest to. 1 was the one we had before, 25, 50, 75, 100, 125, 150, and 200. And you can see how they kind of work. So the bigger your number is, the more time you spend exploring, right? And the exploring is this kind of initial phase where you're picking up a huge amount of regret. You're kind of doing the maximum possible regret per turn because you're just picking all of them equally. So you have all of this regret. Before, it was a tiny bit, right? So when we did it with 1, it was just like a little tiny boop over there. But now if you want to do a lot of exploring, you're going to pick up a lot of regret over here. So for example, if you chose n equals 250, the biggest number, you spent 250 rounds exploring. Ooh, it occurs to me this n is different than the other n before. This n is the number of rounds you spent exploring, whereas the n we did was the number of times you did each one. Okay, so they're slightly different. They're related by a factor of 20. But okay, same principle. Like the longer you spend exploring, the more time you spend in this phase at the beginning where you're getting a lot of regret. Okay, so you're getting some huge amount of regret. The good news is if you did this, look at how little regret you get in the next section. It's almost flat, almost zero regret in the next section. And that's because you spent so much time exploring that you're like very, very confident that the greedy arm is the best arm. So you have a really high chance of the greedy arm being the best arm, and that's why this is almost flat up here. On the other hand, if you don't explore for long enough, so you just do a little bit of exploring, then you have a pretty high slope. So this orange line has a pretty solid slope over here, and that's because we didn't spend enough time exploring, so there's a chance in our greedy phase we picked the wrong arm, right? The thing that is greedy is not the best, and we're picking up explore. When we do the exploiting, we're picking up some regret. So it's kind of like what we saw over here, right? We made the slope less, but the slope is so positive over here, it's not small enough. And then on the other hand, there is this like Goldilocks zone. In this case, it's the green line, where we spent a little bit of extra time over here, but it paid off for us by having a lower slope. So the longer you explore, the lower the slope is in the exploit phase, but the more you have to add on this constant, right? So basically, it's always going to be a linear-ish function, c1 plus c2 times t, but you can tune the values of c1 and c2. So, so here is the punchline. If you explore for n, and then exploit, the total regret, or the expected total regret, it's always going to be like c1 of n plus c2 of n times t, right? And this c2 of n, this gets small as n gets large. This is like the, and I'll say goes to infinity. This is like the exploit slope. And the constant gets large as n goes to infinity. And this is like the explore phase, right? So we can make this constant really, really small, but it costs us making this one really, really big. And our job is to figure out what would be the balance. How do we get the like Goldilocks of the right thing in between? How do we find which of these lines is the smallest? I guess in this one it says n equals 50 happens to be the best here. Okay, so that's what we're going to do. We're going to do some smart analysis and try to minimize the sum of these two things. And if you do it just right, it turns out that the total average is sublinear in t. So if you take the sort of the minimum over all possible n's, by scaling n with t, you can make this whole thing sublinear in t. That's what we're going to try to do. Okay, questions or comments before we start? So this is like some classic like optimization probability type analysis. Okay, and we're going to start with this observation of using the central limit theorem. That's what we're going to do. Here is what we're going to do. We're going to use the central limit theorem to describe what is going on for the averages that we see. And the central limit theorem says that the average that you see is the true average plus some amount of error, and that error shrinks with the square root of n. So I'll draw a little picture to remind you what this is. So the z is some normal variable, some Gaussian random variable, and the average, the central limit theorem says the average you see is centered around mu, and it has some spread with this specific shape. So to show you kind of what that looks like in our simulator, right? If I go to the Bandit simulator and I restart it, right? What it's saying is if I run all of these things for some amount of time, the averages here are 8, 8, 7.8, and 10. Let me make one of them a higher number. Okay, so 8, 8, 7.8, and 8.95. The true average, we don't know. We just know our running average of the samples we have. And the point is, if we have the running average, we can sort of estimate how far away is the true average. it should be 1 over square root of n away. So 1 over square root of 4 is 2. Wait, square root of 4 is 2. 1 over square root of 4 is 1 over 2. So the true average is probably between 7.5 and 8.5 for this one. And the true average for this one is probably between 7.5 and 8.5 as well. This one, it's 5, so it's a little bit smaller. So it's somewhere between like let's say 7.4 and 8.2. This one, because n is larger, the true average is much closer to this 8.95. So maybe it's like between 8.8 and 9.1. And that is the theorem we're going to use to control these exploring phases. So we can kind of get a sense of like exactly how good our exploring is by the size of n through the central limit theorem and the square root of n. Yeah?
What is UCB?
Yeah, I'm going to explain that later on, yes. This is the UCB is going to come up later. Actually, I guess I can explain what the UCB is now. UCB stands for upper confidence bound. And the upper confidence bound is this side. So the upper confidence bound is like pick some percentile and say how hard you have to be for there to be only a 10% chance, say, to be larger than that. That's the upper confidence bound. So all of these things that I'm showing over here, the upper confidence bound, it is the mean plus some amount related to the average. And you'll see like over here I added 2.4, but to this one I only added 1 into it, 1 point something. And that's because this one has a much higher n. So the UCB it'll get closer and closer to the average, and the distance is like the 1 over a square root of n.
Is it the upper bound of the confidence?
It's the upper bound of a confidence interval. The upper confidence bound. Yeah, that's right. Okay.
What significance will it?
Well, you'll see what it is later. Yes, this is good. Yeah. Okay. Okay. Right. Any other questions? Okay. So we're going to bound using this, and so the thing we're going to use is that with high probability, the average is close to the true average mu. The running average is close to the true average. Okay. So the probability that it's between a over square root of n and on either side, so between mu minus a over square root of n and mu plus a over square root of n, that is approximately some amount. And that amount depends on just the area of these little things. It only depends on a. And so we're going to use this version of the central limit theorem that says the probability that the average is between the mu minus a over square root of n and mu plus a over square root of n is at most 1 minus e to the minus a squared. So here I replace them with c's. So this is a version of the central limit theorem called Hoeffding's inequality. Hoeffding's inequality. The reason it's an inequality is because it's at least this much. So no matter what crazy random variable you have, it will at least be like this. If it was a normal distribution, it would be like exactly equal. And if you come up with some like weirdo distribution of fish at the lake, then at least this one will hold with a greater than or equal to. And so what this tells you is that if you make the little regions really, really small, then there's a really high probability that the average is somewhere in there. Okay, so this is a version of the central limit theorem. If you have not taken a stats class, this is going to seem really wild and crazy. So I think everyone's taken a stats class. I don't know how much time they spent on the central limit theorem. I don't know. I think they should replace the whole course. It should just be called the central limit theorem. That'd be a good course name. But I'm not a statistician, so I don't get to choose. Okay. Okay. So here's what we're going to do. We're going to make a definition. We're going to say our exploration phase succeeded with error at most c over square root of n. And we're going to say that when every single arm is within c over square root of n for every single arm. So what this is saying is, back to the little example over here. If I restart this, I'm going to do my explore phase. Let's pretend I do each one 5 times. Okay, and I have these averages that I see, 6.4, 5.2, 4.8, and 5.6. Either all of these averages are close to the true averages, or at least one of them is not close to the true average, right? And the inequality we just did tells us at least the probability that it worked, that all of these are close, we can bound that probability. And so when that happens, we'll be very happy because we'll know that we are in business. Okay, so the probability succeeds, the probability the exploration is successful is at least 1 minus L times e to the minus c squared. Each individual arm has a chance e to the minus c squared of being wrong. And so the chance that all of them are right is 1 minus L times e to the minus c squared. So there's some chance all of these things are good, like they're close to what we want, and there's some chance one of them is off. Okay? So those are the chances we're talking about over here. Okay, and now we can do some analysis. which is if we succeeded, then when we do the greedy phase, we're going to get no more than 2 times c over square root of n regret in each round. So what this is saying is, as long as we succeeded over here, and all of these numbers are close to the true means, then when we go to do the regret analysis, we can control the slope of this regret phase is not more than 2 times c over square root of n. So the slope has to be quite low. Okay, this is a simple argument. So the reason this works is the difference between the greedy arm and the arm that we chose, so like the best possible arm and the greedy arm that we chose over here, it can't be more than mu star minus mu a. Well, mu star is close to the average star, and mu a is close to the average a, so these two things can't be far apart, right? When our thing succeeds, basically, all these numbers over here are close to their true averages, and so how far apart could we're going to pick this one and do it over and over again. If this one's wrong, that means that one over there must have been the best one, and these aren't too far apart. So we can't be too far off. That's basically how this works. A simple little inequality. Okay. Question? No? Okay. Okay, so let's put all this together. So we have this idea. We're exploring for a while. We have this notion of how good was the exploration, and we can measure it with the constant c, right? So we get to choose how long to explore. We get to choose our threshold. What should c be? And we know that if things work out, that the slope of the greedy phase is not too big. So let's put all of this stuff together. So what is the total regret? There's 3 parts, okay? There's the part from the explore phase and the part from the greedy phase, and the part from the greedy phase has 2 parts, okay? The part from there's the chance that it succeeds. When the explorer succeeds, we get some regret, and then when the explorer fails, we get some regret. And we got to combine all these things. So altogether, we have 3 terms. We have this NL, because we spent L rounds for each arm. We did N rounds for each arm. There's L arms. So NL is from the explore phase. And then we have these factors e to the minus c squared. That is the chance that the explorer succeeded. No, that's the chance that the explorer failed. Okay, so e to the minus c squared is the chance the explorer failed. And then so t times L, this is like how much regret we get when things go horribly wrong. So small probability chance, but when it happens, we really pay the price. We get a huge amount. And then when the probability it succeeds, then we get this no more than 2 times c over square root of n times t. And that's exactly the slope of this line times how long this picture is. So if I go back to the picture over here, so the slope is no more than 2c over square root of n. So how much regret do we get? Well, it's no more than 2c over square root of n times capital T. So we have these 3 things, and now we have a bound, nice bound, on our thing. Okay. Very nice. So this is bounding the expected total regret. Now we can say which value of n is the best. We can finally figure it out. Before, it was like some kind of like nebulous thing where like, look, when n is too small, that's bad. When n is too big, that's bad. When is n the best? Well, what we should do is we should maximize this equation. Now we have a nice formula. And this is why they made you take calculus class, so you could maximize this thing right now. How do we maximize this? It's a sum of 3 things. Remember, t and L were given to us. Those are part of the problem. Our job is to come up with c and n. We actually only care about n at the end, and c is like a tool we use like halfway. But you got to figure out for what value of n and c is this equation minimized or maximized. How would you do it? This is a hard one. Yeah, because there's only one variable. You take the derivative, and then you're happy. But it's 2 variables. So how do you proceed? How do you make it work? Anyone have any ideas? What would you do if this was calculus class and they're like, find the minimum over all possible n's and c's? Yeah.
Set the gradient to 0?
Yeah, the gradient to 0. Yeah, you could definitely do that. So it's 2-dimensional, and you hope that if you take the gradient with respect to both n and c, then you do it. When you do the gradient, you're going to get like a derivative with respect to n, a derivative with respect to c. You're going to have 2 equations. And then what are the equations going to look like? It's going to be like L. This one's going to be something. They're going to be equal. So I think when you do the derivative with respect to c, that's going to be a real nasty one because of this e to the minus c squared. So it turns out if you do this one, I think it'll be tough. That's how you would do it in a computer. Put the gradient, set it to 0, have the computer solve it. But let's say we only want to figure out sort of like roughly like order of magnitude, like n and c. How could we do it? This is like, maybe you've never seen this trick. There's like one special trick. that comes up in calculus class sometimes. Okay, I will tell you the trick. The trick is called the equipartition theorem. So we want to minimize this. So here's what it is. It says if you have a sum of three things and you want to minimize it, the minimum happens when all three things are about the same size. Without even knowing this principle, you might have seen this in calculus class. It's like you have a triangle made of wire and a square made of wire. Find the minimum area for both of them. And the minimum area happens when they're both about the same size. Like if the triangle is like way bigger than the square, that's not good. If the square is way bigger than the triangle, that's not good. They should be about equal. This comes up in physics as well. So particles, they have a potential energy and a kinetic energy, and it turns out they kind of hang out in the region where the kinetic energy is equal to the potential energy and so on. So equipartition principle. And so for us, that would say all these three things should be about the same size. Let's try to do this and get some nice simple equations and figure out what they've got to be. So the first term, the second term, and the third term should all be about equal size. Remember, in our problem, these things actually have nice interpretations. And what it's saying is that, look, if we're doing things right, the amount of regret we get from exploring and the amount of regret we get from greedy should be about the same. Like in our picture over here, right? You don't want to do one of these like extreme things where you go like way high and then get like a super like little tiny bit in the next phase. You want to sort of split it equally. You want the amount of regret here and the amount of regret from the next phase should be about equal. Like this orange one kind of does it. A little half the regret is there and half the regret is there. Split it equally. Yeah.
Sorry, what is it when the explore succeeds and when it fails?
Okay. So the explore succeeds or fails is just did we correctly identify which was the best arm in the thing. So and the way we're measuring that is we're measuring it by saying did we get it within C.
So why is there any regret when you succeed? Because wouldn't it?
Yes, okay, so succeed means we measured every arm is correct up to this error C, right? And every single arm could be correct up to error C, and we could still sort of have the wrong arm, but that's okay because the best arm is no more than 2C away from the arm we're at. Yeah, let me draw a little, actually, here's a little graphic that might help you, right? So you have all your arms. Here's like arm one. Let's just have a two-arm situation, right? And they both have a true mean. So here's like mu1 and mu2, and we're trying to measure what these are, and we're saying it succeeds if our measurement is within C of each of them, right? So our measurement is somewhere in here, like this maybe. So here we've succeeded. Our measurements are close to the true values, but it looks like arm 1, even though mu2 is better, the measurement, the average of 1 was higher than the average of 2. So this is a situation where the measurement succeeded. We were like measured well for all of them, but we chose the wrong arm. But it's okay because we're not too far off, right? The only reason it worked out this way is because these two things, there's no more than 2C difference here. And that's the 2C that appears in the slope. So yeah, that's a great question. Okay, what was I saying? Any other questions or comments? Okay, equipartition, I think is the last thing that I said. Let's find the equipartition. Okay. Yeah, we want all these things to be about the same size. We don't want one of them to be much bigger than the other one. Okay, so now we can solve. You get some very simple equations. So n times L, that's the exploring. T times L times e to the minus c squared, that's like when things go wrong. T over c over square root of n times c, that's when things go right in the greedy. Okay, so we want these to be equal, so let's solve them. Actually, let's do this. I think let's try to do this by hand. I don't remember how this goes, so this will be exciting. N times L, that is approximately, what do we say, T times L times e to the minus c squared over 2. That was one of them. And the other one is n times L is approximately, and the other one is c over square root of n. 2c over square root of n times t. Okay, great. Hey, this one's nice. You can cancel out an L. Look at that. And that says n should be approximately t times e to the minus c squared over 2. So that's a nice equation for n. Let's just take that for n and put it in on the other side. So, yeah.
Where did the c squared over 2?
Where did the c squared over 2 come from? So the c is like how far we want to be, right? The c is like specifying what is our tolerance for the error. And then once you specify the tolerance for the error, you convert it to a probability by using the Gaussian normal distribution. And that's where C gets converted to e to the minus c squared.
Wait, you have, is that your or is if you have minus c squared also? So you can
Yes. Okay. Well. Okay. Let me draw the picture. So if you have a standard normal distribution and you have some distance c, the area of this spot is approximately e to the minus c squared over 2, and that's what we're using. So the bigger c is, the smaller the area in this little area, and the bound is e to the minus c squared over 2. Let's go to the slide and take a look at what it was. Oh, okay. Maybe there's no 2. Let's see. What is it? Is the 2 somewhere else?
I guess you can just absorb it into C.
Yeah. Okay. Look, the way I stated Hufting's inequality. There's no 2. Let's do it without the 2. Yes. Okay. Very good. Okay. So the bound, I guess, is not over 2. It is just with no 2. Okay. So here, let's erase this. Okay. So it came from our inequality, e to the minus c squared. Okay. Even better, because now I don't need to deal with the 2. Okay, so I'm going to plug this one in. Why don't I cancel out a square root of n first? So there's a square root of n here and an n here. I can make that an n to the 3/2 times L is approximately 2c times t. Okay, and then now I want to plug one of these equations into the other one. I guess the n is easy to plug in. So it's t to the 3/2 times e to the minus 3/2 c squared times L is approximately 2c times t. All right, so we got a t to the 3/2, and we got a t over there. Those can cancel out. So I plug that into that. Now I cancel out these things. Do a little mini cancellation over here. And what do we get? Let me write it on the other side. E to the 3/2 c squared. L is approximately 2c times what? T to the negative 1/2? T to the negative 1/2. Okay. All right, here's the thing, right? Whatever c is, that's going to be a lot bigger than e to the minus c squared. So e to the minus c squared, I don't know, I put the 3/2 somewhere crazy, didn't I? No, there is a 3/2 there. Okay, so there is a 3/2. Okay, very good. So this c is going to be a lot bigger than e to the minus c squared. So e to the minus c, whatever c is, this thing is going to be way smaller. So you can figure out from here. Maybe I'll skip some of the gory details and just go to the punchline. But now you get a flavor for where these numbers come from, right? There's like a 3/2. This is going to make a square root of a log of here. What's the answer? The answer is, drum roll, n equals t to the 2/3. So that's what you end up with. The 2/3 is the 3/2 flipped on its head. And c is 1 over the square root of 1/3 log t. And that makes the sort of equalities appear. So n equals t to the 2/3 plus a little bit. This log t to the 1/3 is super teeny tiny. So for example, if t is 1,000, 1,000 to the power 2/3 is 100. So spend 100 rounds trying stuff. And then what is the log of t? Well, the log of t is 3. So then spend 3, multiply that by 3. So 100 times 3. And this kind of matches what we did before. So t to the 2/3 is the right kind of thing you should keep in mind. And t to the 2/3, you can see it here. That would say that you know, something of length of 1,000, you want approximately 100 steps. So 100, 50 or 75 or 100 is about right. I guess, yeah, this one's a little messed up because n was the total number, whereas the n before was the number per each. So maybe I should divide them by 20 to make it match. Let's divide them by 20. And do it again, because they were, that's the conversion rate. Okay, here we go. So we want an n is around 100. Okay, maybe it's the other way. Okay, well, I'm going to stop, but quit while I'm ahead. Okay, so t to the 2/3. Okay, we did it. What is the total regret you get when you do t to the 2/3? It is, after a little bit of work, you plug in what this is. You should get a total regret of only t to the 1/3. So let's do that. Well, I guess it's n. One way to do it is it's n times L. All of these things are about equal. Okay, I lied. It's not to the 1/3. It's to the 2/3. So let's write this down on the board, and then we'll be happy. Okay, so we're going to ... skip some steps. ... So I gave you the main ideas. Solve to get the best answer is n is approximately t to the 2/3. That's the best thing you want. Other log terms and stuff are less important. This is the main thing that you can get. And when n equals t to the 2/3, the total regret is also this. The regret is also approximately L times t, or approximately L times t to the 2/3. Okay, which is sublinear. This is amazing. So this says if you play for 1,000 rounds, you should expect only like some hundreds of regret. If you play for 1,000,000 rounds, then you expect only like tens of thousands of regret. So the sort of the fraction of the time you get regret is going down. Very nice. Okay, that is the explore. This is all for the explore n, then exploit strategy. And we did the analysis. We basically found, roughly order of magnitude, what is the right place to sort of bend your curve. You don't want to go too soon or too late. We figured out t to the 2/3 is the right amount. Okay, and I think I have some. Okay, there's a plot over here. Same plot, but it's giving n as a power of t. So you can see exactly this 2/3 is the red line. That's the best one. Right, 2/3 is the best one. Okay, very nice. You might also ask a question, what about epsilon greedy? That is what we've been using so far. Epsilon greedy is kind of exactly the same as this, except for your explore phase, instead of being all at the beginning, is sort of spread out equally. But it is identical. So the right thing to do, if you're trying to figure out the right epsilon value, the best possible epsilon value, if you do it as a power, it's also this 2/3 power. So the 2/3 power is the best one. Let's see, where is the 2/3 power? Or is it the, it's the 1/3 power. Okay, yeah. Okay, let me write this down. Why is it the 1/3 power? So let's compare to explore. Compare to epsilon greedy with epsilon equals. We're going to do 1 over t to the power p. So if you're writing your code for your tic-tac-toe game or your final game, and you're doing your epsilon greedy, you might do the schedule thing where you make epsilon smaller over time. You make it bigger at the beginning, you make it smaller at the end, and you might do it with a power. So you might say, for example, if p equals 1, then epsilon is 1 over t. So if you're on round 100, you do epsilon is 1 over 100. If you're on round 200, you do 1 over 200, and so on. What is the total number of amount, total explore amount? Explore amount. Okay, so if epsilon is 1 over t to the p in round t, how much did you explore in total? Well, it's going to be the sum of t equals 1 to t of 1 over t to the p, right? So the chance you explored in round 1 plus the chance you explored in round 2 is this sum. And this sum is approximately the same as this integral. So this is the fun part of math when you just make up what you want to be true. This is approximately this integral. And what is this integral? Well, it's approximately t to the power p plus 1. Negative. This is t to the, okay, let's write it down proper. Make sure I don't get my minus 1s wrong. So this is t to the negative p. So you should do 1 minus p. And there's some constant. I don't care about constants. So it's t to the 1 minus p. So the total amount, when you do this 1 over p strategy, the total amount you will explore is t to the 1 minus p. So this is like the situation where n is approximately t to the 1 minus p. Okay, so when you do this epsilon strategy, you're essentially exploring t to the power 1 minus p rounds. We said the optimal amount was 2/3. Optimal is n is approximately t to the 2/3. So what is the optimal value for p? Therefore, the optimal p should be optimal p is 1/3. P equals 1/3. So when you put p equals 1/3, by the end of all the rounds, you've done t to the 2/3 exploring, and that is what is being shown in this little graph over here. And again, this is all sort of like up to constants and stuff, but this is in some sense the best you can do. So when you're doing these epsilon exploration algorithms, the best exponent is the green line, which is t to the minus 1/3, p equals 1/3, which is a nice line over here. It does a little bit better than the other ones. So that's a good setting for your epsilon. Yeah?
If instead of using a schedule of that 1 over t to the p, better than that?
That's a good question. I don't think you can. Yeah. So in some sense, if you're going to do this kind of like pure exploration, the best thing you can do is have some strategy that explores t to the 2/3 somewhere. And if you want to spread it out with epsilons, or you want to like do it some other way, but that's like the best you can do. So yeah, this is a good question. Okay. Now here's a question: can we do even better? So what could we do? How could we do even better? So far, we've been doing these strategies of some mix of explore, we either explore or we exploit. But those are the only two things we've done. So far, we've done either pure explore or pure exploit. Those are the things that we did, right? Either you pick the greedy one or you pick one totally at random. Could we do something even better? And we did talk about this a little bit last time, but does anyone have an idea or remember what could we do that's something that's smarter than one of these two options? Something that's better than either a pure explorer or a pure exploit. What would be an alternative? What could you do instead? Yeah.
Like instead of doing a totally random
Yeah.
explore, you could do like one that was like not that bad.
Yeah, exactly. You do something kind of in between. So do don't pick the absolute best one, but let's not pick like the worst one. Let's pick like somebody who's like promising but not the best. So like do like a half explore, right?
Like a mean exploration, a mean,
What was that?
isn't like thinking, high rod or slower.
Yeah, that's right. Yeah. So the idea is in a pure explore, all of them have a chance 1/n to be chosen, and we just pick totally at random. It's like we ignore all the information we have. We close our eyes. We're like that one, right? In a pure exploit, we're like whoever's number is the biggest, we pick 100% of the time, right? In a half explore, maybe what we can do is like some kind of balance of we're like, look, let's pick the like better ones more often. Don't pick the absolute best one. Pick like a promising one. And let's learn like more about it. Okay? And this leads us. This is called, if you do this kind of thing. So as soon as you leave the pure explore, pure exploit thing, this is called adaptive exploration. And the idea is, when you tune the exploration, instead of picking totally at random, you explore ones that are promising based on the knowledge you have. So what might this look like? Let's take a look over here at our little simulator. So let me try all of them, say 2 times each. Here is what it might look like. We might say, okay, I've tried all of them 2 times each. This one has an average of 9.5. This one has an average of 9, 7, and 8. Because I've tried all of them 2 times each, my uncertainty about all of these is about the same. So I might as well, pick the greedy one, go 9.5. Okay, I got 9.67. That's still pretty good. Let's do it twice. Okay, now we're in a situation. Okay, this one's now the best. Let's do this one. Let me get into an interesting situation here, and then I'll stop. Okay, here we go. This is great. So this one has a mean of 8.75. This one has a mean of 8.6. We've tried them 4 and 5 times. If we were going pure greedy, we would pick this one, 8.75. If we were going pure random, like explore, we would pick all of these equally likely. But now let's be a little smarter. So these ones have an 8.75 and an 8.6. We tried them 4 and 5 times. We're like pretty confident about these numbers. This one over here is not that bad. It's got an average of 8, but we've only tried it twice. So this one is like potentially has got some promise to it. So why don't we pick this one? We're doing a mix of exploring and exploiting. We're exploring because we're trying something new that we haven't done. We're gaining more information. And we're exploiting because we're not doing this stupid guy who's like the worst, right? Like we're gonna be smart about how we explore. So this is the best choice in this situation. You might notice something else on the board that I haven't mentioned yet. There's another way in which this one is the best. What's the way? If you're a silly computer, you don't know what's going on. Yeah.
The upper bound is high.
Yeah, the UCB is the highest. So the UCB is automatically mixing together the mean and our uncertainty, right? These ones have higher UCBs because they have higher averages, but then because the uncertainty is low, that shrinks the UCB. Because the UCB, remember, is some mix of the average plus the uncertainty. Let me write that down. So e.g., the UCB is a mix. It's the average plus the uncertainty. So here's the average, and then you draw a little normal distribution right around it, like that. And the UCB is like you add on how uncertain you are. This is like the SD, the standard deviation. So the UCB is like that. So if we're really certain, if we have a really small, like a tight distribution, we know it's really centered around the average, then the UCB will be smaller than something that is wider. And this lets us do like a mix of exploring and exploiting. So you could have, maybe you have like your best possible arm. This is like the average with the maximum, but we've tried it a lot of times, versus some arm that is like slightly worse. This is like slightly worse arm. Slightly worse arm, but it has a wide average. A wide average. And then maybe there's like some other arm over here that also has a wide average. It's like even worse arm. Even worse. So that also has something like that. So the UCB says compare the like tails of these things. Whose is higher, right? So this is the UCB for this one. This is the UCB for the red one. So even though the red has the highest average, the purple has the highest UCB because the uncertainty is higher. This is a little bit like, many weeks ago we were talking about going to restaurants and being optimistic. This is like being optimistic. You're like, hey, this one has an average of 8, but we've only tried it 2 times. So like optimistically, it could be better than those ones. And that's why it has a higher UCB. So what is the AI over here doing? I'll tell you exactly what the AI is doing. It always just plays the one with the highest UCB. So if I think I've done it so far. Let's recreate it. So here UCB. Highest UCB is this one. 12.7. Okay, so the 11.5, 11.2, 11.38, 10.7. So the UCB of this one, even though its average is 9.2, because we've tried it so many more times, the UCB for these ones is higher, right? So these ones have lower averages but more uncertainty. So if we're optimistic, these ones could be better, right? So now we switch and we try one of these ones. This one, 11.75, 11.79, 11.8, 11.1, 10.71. Okay, so now this one has the highest UCB. 11.2, 11.3, 11.7. Oh, it's getting close. Okay, now it dropped 10.58. So what is the best one? Now back to D. D, 10.58. Okay, now this one's the best. So we're balancing which one is the highest average with our uncertainty. And did I nail it? Yeah, so 11, 16 to 11, 11, 16 to 11 is exactly what the AI does, is it just always calculates the UCB, and then it just picks the one with the highest. What was the best arm in this case? C. Ha, we did terribly. Okay, but that's how it works. So it's balancing, it's doing this adaptive exploration, and it is balancing trying arms that are promising. So it doesn't just try any old arm, it tries promising arms. What does promising mean? Promising means the combination of the average and its uncertainty is high, right? Either it has a lot of uncertainty or the average is pretty high. We're adding them together. Very simple algorithm. It turns out this algorithm is, in some sense, the best possible algorithm you could get. What do I mean by that? So the UCB algorithm, you calculate this thing, the UCB, it's the average plus, and then there's some constant divided by the square root of n. That's exactly the standard deviation. And it turns out that it has a regret that is t to the 1/2. So remember the regret we got before was t to the 2/3. The regret for the UCB algorithm is t to the 1/2. And there's a proof that says any algorithm achieves at best square root of t regret. So at the scale of like order of magnitude, the UCB algorithm is the best. Any other algorithm will also could potentially can't beat square root of t. Okay, so that's the UCB algorithm. Very nice algorithm. Okay, what do I want to say? There's some other type of thing you could do. Next class, what I'll do is I'll explain how you can use this UCB algorithm to analyze like chess positions and stuff. And this is the name of the Monte Carlo tree search algorithm. And this led to something called Alpha 0. So here is in the textbook. This is some kind of tree of possible things that could happen. You can imagine like they're like chess games or something. And the Monte Carlo tree search algorithm is kind of exploring the tree, and it uses the UCB algorithm to choose which move to make. So essentially what it will do, and we'll go into detail next class, when you're trying to pick which chess position you want to pick, right? So you're playing a chess game, you want to pick which of these moves to think about, you try them, and you think about them for a while, and then to decide which move to think about next, you say, okay, there's all these moves, which moves are promising, but combine it with the uncertainty. So like, maybe I haven't thought a lot about this move, maybe I should, even though this move doesn't seem too good, we should try it because we haven't tried it before. So we're gonna do the UCB algorithm on like a game situation that takes it away from the bandits and makes it a little more interesting. Okay, that'll be all next class. Maybe I will pause here if there's any questions about UCB. Let me write it down one more time. So here's the algorithm, right? So play each arm once and then do whichever has the highest UCB, and then you just do that forever. So very simple algorithm. Instead of being greedy and always picking the average, by picking the UCB, you're balancing, exploring and exploiting in sort of the optimal way. Okay, questions? Okay, let's stop there. See you guys on Tuesday, and we'll pick up with the Monte Carlo tree search and AlphaZero.